Okay, I have started recording. Welcome to the 9th episode of Astrophysics Talk series organized by Istanbul University Observatory. Today our speaker is Demet Kırmızıbayrak from University of British Columbia. She's a PhD candidate. Actually, we know her very well from Sabancı University and from Koç University. She took her bachelor's degree from Koç University in physics. And also she has a double major from there in industrial and engineering. She graduated from Sabancı University master program there, and her title, PhD master thesis title was Broadband Spectral Investigations of Magnetar Burst. She studies theoretical and computational basis of astrophysics, compact objects, high energy astrophysics, and she also does numerical simulations on that. So she will be giving a talk today on exploring compact objects with spectral lines, then, now, and beyond. I believe that it will be very instructive talk. So Demet, is your turn now. You can share your screen and you can start. Thanks for accepting our offer to give a talk here.
Sure. Yeah, thank you. Thank you so much for the offer and the nice introduction. Let me just do this. And, oh, one sec. And I should start the slideshow. Okay. Hopefully this is okay. And I'll open my annotation.
Yeah, it's perfect. We see your slides very well and you as well. Okay,
awesome.
See you then.
See you. Okay, hello everyone. Thanks for coming to this talk. So my name is Demet Kırmızıbayrak. I'm going to be talking about compact objects today, and I'll be focusing on mainly spectral lines, and I'll talk about how we can understand more about compact objects using spectral lines. And I'll take you through a journey of the then, now, and beyond. So I'll talk about some modeling we do, some theoretical work, but also the then, now, and beyond talks about refers to telescopes basically. So I'll take you through a little journey of past, current, and upcoming telescopes, and just talk about how upcoming telescopes provide an exciting opportunity for us to understand more about compact objects, especially using spectral lines. So first of all, I want to just mainly introduce what compact objects are. So compact objects are stars that are at the end point of their evolution. So you can get, based on the progenitor mass, progenitor star's mass, you can either get a white dwarf, a neutron star, or a black hole. I won't be talking about white dwarfs in this talk, so I'll mainly focus on the bottom two. And when it comes to neutron star, I'll focus on magnetars, which was mentioned before, was also about my master's thesis too. And during my PhD studies, I keep working on magnetars because I think they're fascinating objects. But I also talk about a little bit about black holes when it comes to timing analysis portion of the talk. And I'll focus on X-rays because compact objects have very interesting phenomena in their X-rays that I'll talk about. So the telescopes that I'm going to be mentioning are going to be X-ray telescopes. So they're going to be space missions because X-rays don't really reach our Earth. So here's a little outline. I'll start with a little bit of modeling. So I'll talk about how we model magnetar emission when it comes to phase resolved spectroscopy. And then I'll take you through the journey of spectral line detections like I was talking about, from the past telescopes to the future telescopes. Then on the third part, I'll talk about how we can do timing analysis using spectral lines. And I'll talk about our current efforts in terms of improving timing analysis. Then I'll stop with a couple of takeaway messages. So let's start with the first part. So what are magnetars? Magnetars are types of neutron stars. So these are stars at the end point of their evolution. They're very dense just because they're neutron stars, but also they have very intense magnetic fields that are around 10 to the 13 to 10 to the 15 Gauss. And they show lots of interesting X-ray activity. So magnetars have short bursts that are like in order of seconds or so, large outbursts, giant flares. So these magnetars throughout these bursts and flares can actually outshine the entire X-ray sky. They also show interesting phenomena like quasi-periodic oscillations and glitches and many interesting things in the X-rays that we can think about. And some common explanations people have currently, because the bursts, we don't really know why they happen, but some common explanations people have are, for example, changes in the magnetic field of the magnetar, or some crustal activities. Like, for example, because of accretion, there's a surface tension on the crust breaks, and so on and so forth, or some twists in the magnetosphere actually driving things like these two. And what are magnetar spectral lines? So in a spectral line in itself is just a peak or a dip in the spectrum of any astronomical object you can think of. For magnetars, I plot here two different examples. So the one on the right top over here, I hope you can see this cursor, but on the top one is the spectrum of a magnetar in quiescence. So you can see this like little dip over at about maybe 2.5 kV or so. So that would be a magnetar spectral line. And this is just a magnetar doing its own thing. But on the bottom, I'm plotting a couple of detections for a magnetar spectral line during the magnetar burst precursor, actually. And I'll talk about why it's not the burst, but the burst precursor when I talk about telescopes, but it's just about, saturation issues with current telescopes. It's very hard to see spectral lines during a burst because bursts are in principle, way too energetic for many telescopes that we have right now, especially when it comes to seeing spectral lines. But why do spectral lines happen for magnetars? So in general, we see spectral lines, for example, in the spectra of the sun, and these spectral lines will be, for example, depending on the different elements in the atmosphere. But for magnetars, it's a little bit different. What happens is we get proton cyclotron scattering in the magnetosphere. So we have some photons coming out of a hotspot, for example, and they meet with the magnetic field on the surface, and the photons are scattered at exactly the proton cyclotron frequency. So at that frequency, we're able to see a spectral line because of this, because there's just a lack of photons because they've been scattered. But what makes it very hard to see magnetar spectral lines are because, first of all, they're extremely broadened by the gravitational field because these are neutron stars, they're very dense, but also because they're magnetars, they have intense magnetic fields, and that ends up in broadening of the spectral lines as well. So it makes them much harder to detect. Like, even though there have been detections in the past, like I'm showing here, it's actually very hard to see spectral lines in general spectrum for magnetars. But if we're able to understand magnetar spectral lines, then this promises insight into, for example, what the magnetic field is like, what the gravitational field is like, but also we can understand more about the geometry of the emission region and geometry of the field lines. And I'm going to be mainly focusing on these bullet points, the geometry, based on our modeling. And maybe if we understand all of these things together, then we'll have more idea about why these mysterious bursts are happening in the first place, or why the quiescent hotspot emission is happening, or how it's happening. So without further ado, I'll start with the modeling. So this part of the talk that I'm going to be talking about, the modeling, is going to be based on a very recent paper that we published. So you can find that over here, the archive. It was a couple of months ago, I think. So we take a model for a magnetar emission, which is the same model from a 2013 paper, actually. So what we take here is, imagine there's a hotspot here that we're showing by orange on the magnetar surface that's just emitting photons. And we're imagining that there's a loon, or like an arc-shaped magnetic field lines that is going around it. That's shown in pink over here. So the magnetic field lines are going to carry a current with them. So what happens is, when the photon is coming from the hotspot, it's going to meet with this loon, and it's going to get proton cyclotron scattered through the particles in the magnetic field. And a couple of things that we consider when we're modeling, and these are actually unknown. So we're trying to understand what the actual picture is like. So one thing is, for example, what is the thickness of this pink loon that we're talking about here? And that I'm showing by beta here. But of course, the loon itself doesn't have to be really an arc. It could be different shapes. And I'll talk about these possibilities and how we can understand the shape itself too. So, some explanations could be like a helix-like loon, or maybe like a tube-like loon that I'll talk about. Another thing that we do not know is where is the hotspot itself? That's shown by alpha here. So the hotspot could be closer to the pole, closer to the equator. We're not really sure. But, we could just model that using the angle between the rotation axis R and the spot normal N. And then one more thing that we don't know about, and we're trying to fit with our models, is the orientation of the loon itself. Like, is it above the hotspot directly at 90 degrees, or is it like a little bit tilted, for example? That we're showing by phi here, which is the angle between the loon diameter and the spot meridian. So here's the model. Now there's the data that we used. So on the left side, I'm plotting detections of many spectral lines throughout the rotation phase of the magnetar SGR 0418 plus 5729. So in this 2013 paper, they first of all plotted the light curve on the top, but then on the bottom, we can see the energy, width, and the depth of the line plotted against the rotation phase. And The rotation phase is plotted twice here. So it's from 0 to 1. And then 1 to 2 is the same thing again, kind of, just to see what's going on. But what we see here is that the energy, for example, makes a V shape as the star rotates. So things are kind of changing with respect to the spectral lines. And the same goes for width and the depth. So in the beginning, I'll just focus on the energy, and then I'll talk about the width and the depth a little bit at the end. So let's think about why the energy could be doing this V shape with using our model. So what we're thinking about here is, for example, imagine we're starting on the right side, this little video that I'm going to show you, we're starting at the hotspot being on the edge of the magnetar. So the photons are going to come to your line of sight. So imagine you're the telescope detecting, they're going to kind of come out of the page. And when in this configuration, they're going to meet with the base of the loon, which is a little bit thinner. So the field lines are closer in together. So the field in the base of the loon is going to be more intense, which is going to give you higher energy for the spectral line. And let me play this around. So then, of course, the hotspot is going to go through the back of the magnetar. So depending on GR, probably we're not going to be able to see it because it's not super massive. And then on this side, again, we're going to meet with the base of the loon. But once the magnetar is in this configuration, in the front side, I'll just play it again. But once it's in the front side, basically what will happen is it will meet with the top of the loon, which has a larger width to it. So the field is going to be less intense and the energy of the line will drop. And then this will kind of keep happening, sort of. So we see the V shape. And here's a better picture on that. So on the bottom, again, the 2013 paper, the complete phase result spectrum for the line energy versus the rotation phase. So this is just one phase now. So what is plotted here is that the black line, the black points are where there's like lack of counts, basically, and the white is there's many counts. So this little V shape that is black here tells us that there's an absorption line over here because there's no counts. And that's kind of doing this again, V shape in the rotation phase. So with our model, we try to see if we can actually get this behavior. So we tried for a hotspot at 20 degrees from the rotation axis. We imagine the line of sight is at 70 degrees from the equator, and then we're assuming that the hotspot is directly above the loon is directly above the hotspot at 90 degrees angle. So let's see what happens in the video for this phenomena. Our model is going to show up in green in a second. Oop. Yeah, let me play this. So now we're at the back, so we're not seeing much, but once we're on the side, we'll see the high energy part, and then the low energy once we're at the top of the loon, and then again, the other side. So let me just play this again for you one more time so that you can see. The model seems to be following the V shape, basically, more or less. Whereas we wanted to see kind of how sensitive the model is to understanding this kind of behavior. So we tried for a different configuration. So let's assume now the line of sight is at 70 degrees on the right side. So the same thing. And we're assuming that, again, we're at 90 degrees, but now I'm putting the hotspot to be at 50 degrees from the rotation axis, so closer to the equator. And let's see what happens in this configuration. So again, we're going to get high energy on the sides, and then the energy is going to go down and then go up again. But what we see here is that we're actually completely missing the actual V shape of the data. So this kind of tells us that, you know, if you do efforts like this, we're actually able to understand more about what's happening on the magnetar. Where is the hotspot? Same thing would go for phi, for example. You can try to fit for the orientation of the loon, the thickness of the loon, and so on and so forth. Let me keep going. Oh, there's one more thing I want to mention, which is going to come up in the second slide. Is this, maybe you've already seen, but this little second V shape over here at around phases 0.3 to 0.7 or so. So we try to understand if we can see what's going on over there. So we weren't able to, same as the paper by Tiango et al. In 2013, we weren't able to get this double V shape using a single hotspot. But we tried with a second hotspot, same line of sight, but the second hotspot is at 37 degrees from the rotation axis, and it has a bit of a larger field gradient. So the field varies a bit more for that one. And if we do that, then we get something like this, the purple line, which seems to be doing okay. But of course, this is not a very conclusive fit because the data itself is kind of weak, the detection. But I just wanted to emphasize here that if we are able to get more data on phase resolved spectroscopy, then we're going to be able to constrain our models much better in the future. So up to now, I've been talking about the line energy. So now I'm going to focus on the width and the depth. And that's important because the width and the depth haven't been studied that much before. Like, people have been talking about the changing of the line energy, but we were thinking maybe the width and the depth can tell us more about what's going on in this scenario. So we take two cases. One is the one on the left, which is the same model that I've been talking about. There's this ribbon-like balloon around the hotspot, which is like a solar prominence. You can think of it that way. On the right side, we're now taking a different approach where everything else is the same, but the balloon shape is kind of like a tube. So it's like a 3D shape, has a vertical extent to it. And we start with fitting the actual lines that we saw from the paper that I was talking about. So we put all of them together and we saw how the width varies with energy, the line width. And what we see is the width seems to be sort of proportional to the energy. Our best fit for a power law gives us about a power of 1 within error bars. So let's just assume that that's true for a second. Let's just assume that width is proportional to energy. Now I want to talk about two things on the left side here. One is the equivalent width of the line, how that will vary with respect to the two models, the ribbon versus the tube. So the equivalent width of the line has to do with how many field lines a photon will actually hit when it's coming out of the loon. So in either of the cases, because even if there's a vertical extent, the photon is going to have to go through the whole thing to reach our line of sight, the equivalent width is going to scale with the length scale of the loon itself, or of the magnetic field line. Whereas if you think about the magnetic field, which is B here, that's a little bit different because the magnetic field scales with the density of the field lines. So in the ribbon case, that's going to go with the length scale, but in the tube case, that's going to go as the area, kind of length scale to the power of -2. So if you put all of these together, and again, assuming the width goes like the energy, then we get two things. For the ribbon case, we get that the depth goes like e to the power of 0, so the depth is a constant. Whereas if you look at the tube case, then we get that the depth goes like e to the power of -1/2. Now let's go back to the data. Here on the bottom, I'm plotting the actual depth versus energy for all of the lines detected for this magnetar during its rotation phase. So what we see here is that the depth goes as e to the power of -0.5 plus or minus something like error bars. Within the error bars, it seems that the tube case holds true for this one because it doesn't seem to be a constant. So it seems like the actual shape of the loon is different than previously discussed. So it might be, I mean, there's other scenarios we can consider here, like helix, so on and so forth, but it seems like it's just, closer to a tube-like shape. And I should also mention, we are trying to get our models to get these results kind of analytically so that we can fit for different shapes with the widths. So currently, like, we're still progressing the model, but this just kind of shows the power of actually understanding and being able to constrain the width and the depth of a spectral line for a magnetar, and how that can help us understand more about the field geometry near the emission region. So let me keep going. So now I come to the second part of my talk, which is about detecting spectral lines using future telescopes. So I'll talk about a couple of telescopes here, and I just wanted to give you a timeline of kind of things happening. So we had here, the dashed lines are older, like, or current telescopes. So for example, NICER was launched in 2017. We have EXTP coming up, which is a polarimetry mission, but also has a detector called the Large Area Detector, which is pretty huge. So it's going to be interesting to see, because the telescope itself is big, how things are going to be. There's also Colibri that's coming up, and then Athena that's coming up a little bit later. So EXTP is kind of like 2025, and then the other ones are going to come up. So I'll kind of go through a comparison of some of these detectors. Like, I'll use XMM, NICER, not Chandra because it has imaging as well, but many of those ones. But before I do that, I wanted to just give a brief introduction to Colibri, because maybe some of you haven't heard about it, and also because I am kind of involved in the collaboration, the Colibri collaboration. So Colibri is an international-led, Canadian-led international X-ray telescope design. So I think 2 years ago, we finished the concept study. And currently, with a smaller group, we're kind of trying to improve the science of Colibri a little bit more to get to the point of phase 1, which is, when we start to think about building the telescope itself. But what Colibri is supposed to do is kind of shown in the actual logo. It's a hummingbird. Colibri itself is a type of a hummingbird. So the hummingbird will flap its wings really fast, which we use that because, the timing resolution of Colibri will be very high, as well as the hummingbird is very colorful. So our spectral resolution will also be high. And the effective area of Colibri is going to be very high as well, because the main focus of Colibri is to be able to look at the brightest objects in the universe. So we want to get as many photons as possible. So the bigger the detector is, the better that's going to be. And another thing that we do so that we can get as much as possible out of Colibri is we use basically horrible optics. So we make the optics non-focusing, like a bad way of doing that, because we do not want to saturate our instrument. We want to get as much as possible. And, as long as we know it's coming from the source, we're not kind of dealing with the angular resolution in that part. And if anybody's interested, you can find more resources for scientists at our website. We have, for example, response functions and an effective area functions. So, just if anybody's interested in doing any simulations, and you can find some, I put in a couple of white papers about Colibri. We have different ones that talk about how the telescope works and how we'll do the neutron star science, as well as how we'll do like accretion physics stuff. And Colibri is able to get all of this like high throughput, high resolution and everything, and high effective area through a novel technology called transition edge sensors, which have been achieved in lab, but not for detectors yet. So if you want to, this is not my area of specialty per se, but there's a very nice paper from people in our group that talks about test detectors a little bit more. But basically, a test detector is a superconducting metal film that functions near its transition temperature. So once a photon hits, the temperature rises to the transition state, then electrons start moving more slowly. So you have a current drop, and that's how you can kind of detect a photon coming in. And the idea is that the transition edge sensors will be built over here at the University of British Columbia at the Quantum Matter Institute. So yeah, and that's gonna make Colibri able to detect over 250,000 photons per second or so. So it's gonna be an exciting instrument. But with that said, I'll go back to a comparison of all of the telescopes. So here on the left side, I'm plotting the maximum count rate, sort of the saturation limit of different telescopes versus the time resolution. So we can see, for example, and mind you that the Y scale is logarithmic. So for example, Colibri and EXTP, which are upcoming instruments, are more than about 10 times larger maximum count rate than RXTE. And that's going to be very important because we want to see, for example, spectral lines during a magnetar burst, and RXTE was the main instrument I used for my master's. So we did like a whole database of RXTE bursts, like hundreds and hundreds of them, but we did see a lot of pile-up issues sometimes because the burst was just way too energetic. But with Colibri and EXTP, that's not going to be an issue. When we look at the right side, we see that the effective area versus the spectral resolution. So we can see, for example, EXTP's effective area is pretty huge, but Colibri is also doing pretty well. Athena is also similar, but I should say this is from 1 to 10 keV. So about at the lower energy limit, Athena is on the bottom of this plot. So it depends on the comparison itself. But let me just move on to, how our simulations are like. So we wanted to check for some older instruments versus some upcoming instruments, how these detections that I was just talking about are going to look like. So kind of like on the right side, you go to the future over here, or possible future. So these are the same lines that I was talking about for this specific magnetar, SGR 0418. And on the top, I have the depth, then energy, then on the bottom, the width. And we can see once we get to the area of Colibri, Athena, and EXTP, the error bars are getting much smaller. And here's the better way to look at that. This is kind of like more in bulk. So I'm just plotting on the right side here, the percent parameter error. So 1 sigma error divided by the parameter itself. So the blue is energy, orange is depth, and then green is width. And we can see we're getting at least 3 times better at detecting, at constraining the error bars on these things with EXTP, Athena, and Colibri, especially EXTP doing better at the depth and the width. But then, Athena and Colibri are doing a little bit better on the energy. And on the left side, I'm just plotting 2 examples just so that, if you're interested, you can see what it looks like in actual, in real life, basically, where you can see the error bars of XMM, for example, which was the original detection for these spectral lines. They were with XMM Epic PN. The error bars are much larger. And of course, the count rate also scales with that. So this was for quiescent emission. Now I'll move on to spectral lines during a burst. So like I was saying before, pile-up is a common issue because bursts are super energetic. So often the detections for spectral lines for magnetars were done during a precursor of a burst. So we took one example for a magnetar SGR 1900 plus 14, but what we did was we kind of rescaled the normalization so that we obtain a burst-like scenario, about 35,000 counts per 0.2 second exposure time. And we kind of simulated the line that they found, which was at 6.4 keV in this 1998 paper by 2000 paper by Strohmeyer et al. And we just simulated everything using Nicer and Colibri responses. And then we fit things back again and saw how the line width, the fit itself looks like. And we varied the line width so that we can see, like, if the line was broader or if the line was too narrow, how would these things compare? But we kept the flux of the line constant while we're doing this, because physically that should be the case. So you can see here, the simulated ones are the blue stars, and then Colibri is shown in pink and Nicer is in gray. So we can see that Colibri is not only getting better at finding where the actual line width is, but the error bars are much smaller too. So we're able to get accurate and better constraints on the line width itself. But this was just Colibri versus Nicer. Here are a couple of other instruments. So this is again the same burst, same line that I was talking about at 6.4 kV. So we start from our XTE, which is the oldest. So on the bottom, on the right, to the right side, I'm going into kind of the future. GRISM is a more current telescope, as well as Nicer. And then on the top, I have the upcoming future telescopes. And you can see the spectral line itself is showing up very nicely with EXTP and Colibri. And Athena is a little bit harder because it seems here that effective area is the most important when it comes to detecting spectral lines, because EXTP and Colibri have the highest of the effective area. And one way to look at that is also to look at the Y scales here, because they're not the same. For example, GRISM is going up to about 3,000 counts per second per kV, whereas if you're in EXTP land, then we're going to more than 10 to the 5 counts per second per kV. So we have a lot more data. So we're able to find the line, detect the line, but also to be able to resolve the shape, which, going back to the modeling, is going to help us understand more about magnetars or, or astronomical objects in general. And here's another example. It's the same line, but we just wanted to see, because it was at 6.4 kV. So we wanted to check, maybe, EXTP was doing better at that particular energy. So this is the same situation, but we just changed the energy of the line to be 8 kV, and we see something kind of similar. And then the next slide, we see the 4 kV line. So we changed it to now lower energy, and we see sort of a similar case. GRISM is kind of detecting a line, but it's, I'm not sure if this is within like 1 sigma errors or so. But yeah, what's happening is that, with Colibri and EXTP, we're getting to an exciting era of being able to detect spectral lines and understand about them. And just one last example, I think this is a nice example to show you the scale of the count rate and effective area. Here, this is for a pulsar, PSR J18331034. And the blue is the Hitomi detection for the spectral line. And the red and the black ones are for Colibri for 2 different configurations with different effective area. But, as you can see, we're getting to huge counts, and that's helping us understand more things. With that said, now I'll move on to the third part of my talk, which is the last part. So I'll talk a little bit about timing analysis using spectral lines. So, and with that said, I'll mainly focus on time lags in astronomy for this, because this is kind of, I guess, probably the biggest project that I'm working on for my PhD thesis over here. Is about, being able to resolve time lags in different ways and about developing new methods to understand time lags. So what is a time lag in astronomy? It's basically a part of the spectrum, like say a certain energy band, like the photons coming at 6 to 8 kV or something, being a little bit later than a different part of the spectrum. That's what we mean by a time lag. And there's different lags that we see from, for example, black hole binaries or other sources. And these are thought to occur due to different reprocessing mechanisms of photons. A very nice example is reflection, so I'll talk about that in a second. But I just wanted to mention exact causes in general for lags that remain unknown, because there's many different lags we see, and some of them, people are coming up with models or theories to explain, but it's taking us time to understand what's actually happening there. But time lags are very unique indicators of cause and effect in astronomy, because, you see something lagging the other, it kind of tells you, if you see also a relationship, that there's a causal relationship between these two things. But also they're unique indicators of time scales of processes regarding the object. And that's very important, because say we see a lag of 10 seconds between two things, then we know that the process that's causing this time delay has to be within that time scale. So that gives us an idea about what's actually going on in this object that we didn't know about. So in general, time lags in astronomy, they provide essential tools to understand, like I said, the physical processes and emission mechanisms. but also to understand geometrical configurations. And we can also use these as tools to identify different transient behavior that are currently mysterious, like, for example, outbursts of black hole state transitions, jets, and things like that. And of course, we can also use them to estimate important parameters like a mass and spin of a black hole. And I'll talk about this a bit later too, but in general, they will also help us probably to test gravitational theories, especially when it comes to black holes. We get to the high field regime. So we can, for example, if we're able to understand time lags, which I'll talk about in a little bit, but up to the event horizon of the black holes, then we're basically able to test general relativity in the high field regime and see if it still holds true. So that's some of the things, that's like a main goal that I personally have in mind in general for the future. But I'll show you a couple of examples for timing analysis with black holes, spectral lines. So this is one, this is for a stellar mass black hole. This is like a very classic spectrum of a stellar mass black hole. So in the soft spectrum, in the low energy here, we see that the accretion disk is dominating. So we have an accreting black hole, imagine. So there's a disk around it. And the disk itself has a certain temperature. So because of this temperature, it's going to have black body or, some sort of a thermal radiation, basically. And that's for the stellar mass black holes is going to peak at the low energy parts from, I guess, up to 5 keV or so. When we get to the higher energy, what we see here is that now we have the corona dominating. And the corona, what is that? It's kind of an observational fact because we see the corona. It's a blob of, you can imagine, electron-positron pairs that are sitting above and below the black hole. So the accretion disk is kind of like around the black hole, but I'll show a better picture, but the corona is kind of on top and below. And what happens is from the accretion disk, these thermal photons go up and hit the corona. And because of the electron-positron pairs, they get Compton upscattered. So the energy becomes higher, and then they're now reach our line of sight through the corona. And this is a non-thermal emission, so that's going to have a power law shape. So in the a little bit harder side of the spectrum, we see a power law shape. Another thing that's interesting, which brings us back to spectral lines, is a reflection scenario. For the black holes that are accreting, we also have the possibility of the corona photons actually going into the accretion disk and bouncing off and then reaching our line of sight. And this reflection feature usually has a very high spectral line peak near the iron K alpha line. So it's, it's what you see for the accretion, and that's going to peak at around 6.4 keV or so for a stellar mass black hole in general. Here's a better picture of that to help you understand a little bit more of the geometry. So we have the disk. So in one, we have the thermal emission from the disk coming up. So that's one thing that we see. Two is the disk photons go to the corona, get upscattered, and then two things can happen. One, they either directly reach our line of sight, which is shown by 2 here, or they go to the accretion disk, gets bounced off, and then reach our line of sight, which is shown by 3. So the interesting thing here is that between 2 and 3, we will actually see a time lag because the photons in 3 had to travel an extra distance to go to the accretion disk and then bounce off. So based on what this distance is, they're going to be time delayed by a certain number of time. And what's more important is that if we're able to understand, if we're able to resolve what the time lag is, then we have an idea about the scale of the system, about how large the photon had to kind of travel. And that gives us an estimate on the mass of the black hole, because the mass of the black hole is going to decide how large the scale of the system is. And actually, this technique itself is called reverberation mapping, and it's very widely used to estimate, for example, masses of black holes. So it's a widely used technique. And yeah, the artistic impression here is, I think, was JPL NASA, which tells about that. So I'll talk about a little bit more about the reverberation mapping scenario. But one thing I wanted to say was, now let's imagine upcoming telescopes. How could we improve things in the future? Because we're going to have more spectral resolution. We're going to have more counts. So one thing that we can do is to actually slice things up within this accretion disk itself. And then we can see what the time lag is for each little portion of the accretion disk. So if you can slice things up kind of in energy, then we can understand the lags, which will tell us about the length scale for each part of the accretion disk. And if we are able to do that at the end, then we sort of we can understand what the disk looks like geometrically. And if we're able to understand that, then that gives us an idea about the actual space-time surrounding the black hole. And we can go kind of up to the maybe ISCO, the innermost stable circular orbit, and try to understand if space-time kind of behaves in the same way. Or we can also do stuff like estimating the mass or the spin, which I'm showing kind of here. So one kind of function that we can use to be able to see these things that I was talking about is called the response function. So function, it is kind of like the kernel. So it's here, I have a little equation. So I think it explains things a bit more. O here is the original emission, and D of T would be the delayed emission. So the response function, which is R here, would be the thing that convolves with the original emission so that you get the delayed emission at the end. So it's the convolvee per se. And on the bottom here, I'm plotting a couple of simulations for responses that we have made. So this is, I think this was for a Kerr metric, so a Kerr black hole that has some spin, and also like we can see different spin parameters on the bottom here. So I'm kind of plotting the response for different ones, and we're assuming there's a kind of delta delay, delta function, sort of like a response. So what you see here is that as the spin parameter changes, for example, the like near zero on the bottom here is closer into the black hole, more closer to the innermost stable circular orbit. So you get kind of a truncation once the spin is changing on the right side, to the right side here, or the response function itself completely kind of changes shape. And that tells us that we can, for example, estimate the spin if we can get the response. We can estimate the mass. And for example, for gravitational general relativity, then we can use stuff like the no-hair theorem, which tells us that a black hole is going to be explained by its mass and spin and charge, like basically 3 parameters. So we can understand, we can test, for example, that theorem using this as well. And here's more about how we can actually estimate the response function, because it's not an easy task to do. So this is kind of like one of the things for my PhD thesis. One of the things that I was working on was what kind of methodologies can we come up with so that we can actually find the response of black holes. So one method that we're adopting, we're kind of developing for astronomy is called Wiener deconvolution. So it's not a new method per se, but it is new to astronomy. It hasn't been used in astronomy, but it was used very widely in, for example, image processing or signal processing and stuff like that. So on the top here, I have a nice example of that where we have an original image that we don't know about. And then there's some blurring to the image that's, you know, like a response blurring that we do know about, and that gets convolved. And then we use the Wiener filter to get the Wiener deconvolved image in the back, which is an estimate of the original image. And I should also say it's the minimum square error unbiased estimator of the original image itself. When we get to the case of black holes, the situation is a little bit different because we do know somewhat the original emission, or we're assuming that we know, because like I was saying before, like if we take the certain energy band, we know that that energy part will going to come from the corona, or it's going to come from the disk, for example, or the reflection because of the iron line. So that we're assuming that we know, but we don't know in this scenario is the disk response itself, what is being convolved with the original emission to get the response function at the end. So if we use Wiener deconvolution, we kind of do a little change of variables, and we can adopt the method kind of to get the response function at the end. So I'm going to show you a couple of examples of using Wiener deconvolution the way that we've adopted it, at least, and how that helps us understand more about black holes. So this is one interesting example from a 2019 paper by Kara et al. This is a black hole I personally very much enjoy because it has many interesting transient behavior. It's called MAXI J1820 plus 070. So what they found out was that the lags for this black hole, the aberration lags, were kind of changing in frequency. So here, the red one is the earliest observation, and pink is the latest observation. So as time goes on, the lags that they found for this particular accreting black hole went to higher frequencies. And their explanation for this was that the corona is actually shrinking for this black hole, because as the corona gets smaller, then the variability time scale will shorten, so you will go to higher frequencies. So maybe the corona is evolving in time for this particular black hole. And we did want to check this case, I should say, using X-rays, because this is nicer data. So we tried doing that, but I should say, like, our new methodology with Wiener deconvolution is kind of pushing the telescopes to their limit, because we want to get to very low timing resolution to more than 10 to the minus 6 seconds or so. And with NICER, it didn't seem that that was, kind of the case. But what we did was we looked at VLA data. So on the left side here, I'm kind of plotting the bigger picture of the light curve on the top of this particular black hole. And then on the bottom, I have the hardness diagram. So this is the complete outburst, and I think it was in 2018. So the stuff that I was talking about, the corona getting smaller, those were happening in the blue dashed lines. And this black hole had like many different things. For example, the hardness kind of changes, you can see near the green line. So it's kind of changing states from a hard state to a soft state. And very shortly after that, we actually saw a radio flare and jets being ejected from the actual black hole binary. And a little bit later, then it went on to the hard state again, and then it went back to quiescence. So the outburst kind of stopped. So we took it, for example, we looked at the radio data because X-ray was just not working well. And we tried to find lags in that case. So on the right side, I'm showing the response function for this scenario. These are all versus a certain 25.9 gigahertz energy band for VLA. And this would be, of course, radio. So it's a different kind of emission. But so the green parts here are lags that were already found for this particular black hole binary in a 2021 paper by Tetaranka et al. And on the top, I'm just plotting our response function from various different energy bands. So for example, the top one would be 5 gigahertz versus 25 gigahertz. And then the second one is 7 gigahertz, 7.45 gigahertz versus 25.5 gigahertz. And as like you go to the bottom, the soft band frequency will get bigger. So a couple of things that we see here. One, we are able to detect basically the same lags that were found using previous methods, like cross-correlation Fourier analysis stuff. But another thing that's very interesting here is that now first of all, the lags are constrained to like a narrower area, but also the shape of the response function itself now has physical meaning too. So it's not just about the lags we find, but about, for example, on the bottom, the fact that it's way too peaky than the top ones can tell us more about the object itself. And I should also say it's pretty interesting that as you go to the lower frequency soft band, the lags are also kind of increasing too. So one thing that we're thinking about is that we're kind of trying to understand what's going on, is that perhaps it's kind of like an orchestra where like synchrotron radiating little bubbles are coming out of the black hole, and then they emit at a certain frequency, and then they go outwards, and then they emit at a different frequency because they're, say adiabatically expanding or something. So the emission energy changes, and that's going to kind of cause you to have larger lags that's more outwards from the black hole, which is going to come at, for example, a lower frequency. So this could be one of the things that we're considering here, but we're, still developing the models. Another example I can show, I think hopefully I have time, is for an AGN. So for this one, a detection from a 2009 paper by Zogby et al. Was finding soft lags at a certain frequency band at 700 seconds variability scale, and hard lags at 5,000 seconds variability scale. So we wanted to kind of see what this could look like. So we took these two bands, which is 0.3 to 1 keV and 1 to 4 keV, and we first did the cross spectrum. And I should mention cross-spectral analysis is usually how lags are being studied in general, or people do lag frequency spectra or lag energy spectra, but this is like the main methodology that people will use. And you can see that we can maybe get the hard lag over here, but the soft lag is very hard to detect. And what, one drawback of this is that you can only look at lags as an aggregate way. So you get like the complete spectrum itself in the lag. Whereas on the top, I'm plotting our response function. And in this case, we can get the soft lag and the hard lag directly out of the thing, and we can see them kind of together. And moreover, we can see, for example, the soft lag is more peaky, basically is narrower, whereas the hard lag has a different shape to it, which can tell us more about this specific AGN, which is 1H0707495. I think, this is my last example, which is a very interesting thing that we're still trying to understand, but this is for a black hole binary candidate, SS433, and it has multiple spectral lines in its spectrum that we have found. So here you can see, I'm just numbering them by 1, 2, 3, 4. But it seems like, because we're not sure exactly what the spectral lines are, but it seems like 1 and 2 are near where the iron line would be, near 6 kV, and 3 and 4 are near nickel lines for the specific source. And we do know for this source from just the jets that there is actually nickel. So it could be possible, but we don't know, for example, because one thing that is confusing is that it's not just one line. Each of the lines are actually a double peak feature. So why are there 2 iron lines? Or is it, for example, a combination of iron and something else for the second line? So that was one thing that we were trying to understand. So what we did was we basically generated the response function with the same Wiener deconvolution method. And we did that for 2 cases. So the top one is kind of a control case. So we're doing lines 1 and 2, which we think are iron lines, and lines 3 and 4 together. And we're doing this because we think what might be happening here is that maybe the lines on the left are both iron lines, but they're just Doppler shifted back and forth. Whereas the lines on the right maybe are nickel lines, but they might be Doppler shifted too. And if that's the case, then there should be no lag between the iron and the nickel lines, because, you know, that's not what's happening here, but there should be lags between the left lines and the right lines, because the left ones would be Doppler shifted one way and the right ones will be Doppler shifted the other way. And that's exactly what we saw when we looked at the response, because in the first case, we see that the response peaks at 0 lag, whereas on the bottom, we actually there's definitely not a peak at 0 lag, and we get an actual peak at 10 seconds. And we're not exactly sure yet what the 10 seconds mean. We're still going back to the model itself and trying to understand if it actually does hold true for a Doppler shifting scenario. But overall, we do see an actual lag between the left and the right line. So that tells us that it might actually be the case for this particular source. Just to end things, I just want to say, in terms of timing analysis, future detections are going to get much better too. So it's not just spectral analysis, because first of all, the response errors for Wiener deconvolution, they scale with the count rate square, but they square with the exposure time. So you could make, for example, a nicer observation as long as you want, but that's going to help you up to a certain extent. But if you're able to get more count rates for the response function itself, then that's going to go as the square of things. So you're going to be much luckier to find, for example, lags and the shape, to resolve the shape of the response itself. And what's going to help with that is, of course, high effective area, because the bigger the telescope, the more counts we have. And also what's going to help is to looking at bright sources, because then there's just more data to look at. And of course, to look at transient behavior too, because, say if it's an outburst, then we're going to have more counts too. And for those things, we also need a high throughput so that we're not, going to the pileup limits and anything. And also lags usually come in short time scales. So for example, for black hole binaries that are of stellar mass, the reverberation lags are going to be in the order of milliseconds, sometimes even less, 10 to the minus 4 seconds. So your timing resolution better be much less than that. So, future upcoming telescopes with higher time resolution will help things. And also, if we're able to, I was talking about for the accretion disk, if we can resolve things very finely in energy, then we're able to get to the response of the whole accretion disk and see the accretion disk kind of geometry. So for that, we also need high spectral resolution. So, Colibri, XCP, and Athena, and other upcoming X-ray telescopes are providing a lot of exciting opportunities for us to look at compact objects in general. So here are 3 takeaway messages from my talk. One is, like I was saying, higher effective area especially is very important, but in general, upcoming new telescopes are opening up an exciting new era to look at spectral lines, lags, and compact objects in general. The second takeaway message I want to give is that, from the first part of my talk, is modeling and constraining spectral line energy, but also the width and the depth that I was talking about here concurrently would help understand magnetary emission, especially when it comes to the geometry. And last of all, the upcoming novel methodologies will help us understand more about accreting black holes and search for new lags with higher accuracy. And I should also mention, this is not the only method that we're kind of working on. And we're kind of getting to the point of we're almost ready to submit the paper. So within the next coming months, you're going to hear more about our novel methodologies, Wiener deconvolution, and some other stuff. So yeah, thank you for listening. That's all.
Thank you, Demet. It was very nice talk. It was very fluent and nice talk, and it was like 3 talks at once. So it's bonus for us.
Yeah.
So if there is any,
I tried to put it all together.
yeah, but it's okay. So if there is any question from audience, we have time for that.
I have one.
Sure.
Demet, thanks a lot for the talk. I have the question for the first part of your talk. For the proton cyclotron line, what kind of a magnetic field strength do you assume, or I mean, is that
Oh yeah, I can just
depend
show
actually?
you. Yeah, one sec. I actually have, I think, a backup slide for that. Let me just find. We're using the same parameters from the Tiango paper from 2013.
Oh.
So the Bmax would be the base of the loop would be 10 to the 15 times 7 Gauss. And F is the gradients throughout the loop for the field.
I see. I see.
You can see it, right?
Yeah.
Okay.
Thanks a lot.
Sure.
So,
But yeah, for the second hotspot, F is different. So I kind of wrote that down in here too.
okay, I see. So when you actually decrease the strength, how does it change then? I mean, like the line energy and so on should be moving around, right?
Yeah, exactly. It will go down basically if you have less. So
Because I remember you had a few slides showing the energy of the line, the expected energy, let's say, in your simulation. So in addition to these geometrical parameters, the energy will be depending on the magnetic field strength as well, right?
For sure. Yeah, it's going to kind of shift things up or down, basically. So you can get the field strength, from this as well.
And is this valid down to, I don't know, maybe 10 to 13 Gauss levels and so on, or this model, can it be applied to lower magnetic fields?
Yeah, I don't see why not. Yeah, I think it should be. We're just, what we're basically doing is just using the topology of the magnetar to get to, the angles and everything. And we're just using the Belaborodov approximation to get light bending and nothing specific about the field intensity, I think. So I think it should be robust.
Because there's this, you may remember, central compact object, the 1207, which shows 3 proton cyclotron lines in its spectrum. Actually, it's a little old source, was first realized back in the first times when Chandra started working. There's one proton cyclotron line. I mean, people claim it to be proton cyclotron, let's say, at 0.7 keV, and then a harmonic at 1.4, and then a third harmonic, actually 2.1. Showing phase resolved evolution as well in its persistent emission in the sources. And it's actually, I mean, if you see, you can look through like 2002, 2004 kind of years, papers. The lines are really, there obviously, and so on, very significant actually. The only discussion was that it's a low energy, so was it really a proton cyclotron line or something else and things like that? But there is this 3 harmonic.
You can make this electron cyclotron too. You would just need to change the masses and stuff. And I think you could basically change the model so that you can get to that.
Yes, but then for then the magnetic field strength should be really low for you to have lines at soft X-ray bands, because at 10 to 12 Gauss level, already electron cyclotron line is about 10 keV. But for proton cyclotron lines, it is much more feasible. So anyway, so I want to remind you that source, maybe, I mean, I don't know if such plots have been made for that source, but it is really easy to extract actually. I mean, to see already by naked eye, let's say, in the X-ray spectrum, the lines and stuff, it's very much obvious. So I thought maybe it would be a good source to apply this model to see how it
no, yeah, that would be perfect. Kind of like we're looking for more sources and more data to kind of test the model too. So does it have kind of like an evolution like this of the line?
This
we
is
can look for like over the
energy.
phase
changing.
No,
in that source, I mean, as far as I could remember, in that source, the lines are kind of fixed at 0.7, 1.4, 2.1 keV. But shows the phase resolved evolution in width and sigma, width and amplitude actually.
Okay.
So, I mean, you can look at the papers and maybe in detail, there may be something that's, differentiating these two sources. it's definitely not, I mean, it's as I've said, it's definitely not like SGRO 418 where, you know, it showed one outburst and then kind of declined and stuff. It's a more persistent source, but much more quiet, you know, on average. So it's a different source, but maybe interesting for you to take a look at.
Yeah, that would be very cool. Yeah, I can maybe follow up on that too. Get the papers. Yeah, thank you.
Is there any other question? If not, actually, I would like to have a question to you, Demet. Again, from the first, but can you go to next slide where you have a line width versus emission geometry? Yes, you have the observation output there at the right bottom, and we see that the width, the energy kV, it's the width, isn't it? The x-axis.
For the bottom plot?
Yes.
It's energy versus depth. Depth is on the y, energy is on the x.
So line width can go up to 4 kV then?
No, energy is on the x-axis. So 4 kV would be the energy. The line width is the top one. I don't know if you can see my cursor. Can you?
Yeah, we can.
So this would be the line width. So the width goes up to 2.25 kV.
Oh, okay.
The energy is from 1 to 4 kV because we're taking the first line over here. So the energy kind of moves in that direction.
So it seems like at around 4 kV, you see the depth of 0.6, something like that.
Yeah, 0.5 or maybe.
Okay.
Yeah, exactly.
Because sometimes it can be a mathematical issue if you have such large line widths. It can fit all of your model. So basically, it means that your model is somehow not very correct, and you correct your model by using a large Gaussian. So it gives you the large equivalent bit of the line, but it's not the case here.
Yeah, I don't.
Okay, good.
I should say, the data itself, I haven't fit because it's from the paper itself, so it would be their fits, but I would think that they're pretty valid because, like we can see over here too, kind of the shape going as the V line, like the energy and so on and so forth.
Okay, and also I have a comment for the source that you would like to work on, Maxi 182007.
Yeah.
You showed it at the end. I think still the largest database of this source is the Chinese satellite HXMT, and there are public data, so you can also have a look the inside HXMT data of this source.
Oh, okay, I haven't thought of that. Yeah, I should check that out. We were always looking for mostly nicer data because we thought the timing resolution would be nice. I'm not sure for that telescope what is the timing resolution is like, but I can check that.
At least in the high energy band, it's quite good.
Okay.
I don't remember exactly the number, but it must be even better than nicer, maybe in the high energy.
Okay. Yeah. Thank you.
So, So if there is no any other question, we can finish our talk for today. So thanks to our speaker again for this very nice talk and for accepting our offer. So see you on next Monday.
Thanks, Demet. See you.
Bye for now.
Nice to see everyone. Bye.
Bye.